Waveguides problems part 2 on parallel plate guides, rectangular waveguides and circular waveguides. The properties and characteristics of waveguides, they are studied under various heads like filter characteristics, dispersion characteristics, modal propagation characteristics, impedance characteristics, etc. When I say waveguides, I mean all including parallel plate guides, rectangular waveguides and circular waveguides, hollow pipe waveguides in general. In the present session, we focus on problems set around the characteristics of these waveguides. To begin with, we consider a problem, example 1. Determine the cross-sectional shape, dimensions and cutoff frequencies for dominant mode of operation of the following waveguides: WR1500, B WR15, C WC 528, D WC 14. Solution. The number in the designation indicates broader wall dimension in mils divided by 10 in case of rectangular waveguide. In case of circular waveguide, the number is diameter in mils divided by 10. He is talking about this 1500, 15, 528 and 14. These numbers carry certain meaning. Okay. Now, when it comes to designation, R indicates that this designation pertains to rectangular waveguide, and C in the designation indicates that it pertains to circular waveguide. Okay, so first two, A and B, are rectangular waveguides, C and D are circular waveguides. Now we go to A, WR1500. In this case, broader dimension is A equal to 1500 into 10 into 25.4 into 10 power minus 6. It comes out 38.1 cm, and the other dimension B becomes, B is A by 2 usually. In standard waveguides, this is the case. B is 19.05 cm. Thus, A by B is 38.1 by 19.05 cm. Cutoff frequency for dominant mode of operation of C is C by 2A. So, 3 into 10 power 10 by 76.2, it comes out 0.393 gigahertz. Bandwidth is from 125% to 189% of cutoff frequency. Hence, it is from 0.4912 to 0.743 gigahertz. B, when the waveguide is WR15, in this case, broader dimension is A is equal to 15 into 10 into 25.4 into 10 power minus 6. It comes out 0.381 centimeter. The other dimension B is A by 2 equal to 0.1905 cm. A by B, therefore, is, these are dimensions, 0.381 by 0.1905 cm. Cutoff frequency for dominant mode of operation. Actual formula is FC is V by lambda C. This is the formula, V by lambda C. In the present case, V equal to C, lambda C equal to 2A. So it results in 39.3 gigahertz. Bandwidth, as already mentioned, it is from 125% to 189%. It comes out 49.1 to 74.3 gigahertz. Now C, WC 528. C is that, therefore it is circular waveguide. In this case, diameter is D equal to 528. This 528 is this number into 10 into 25.4 into 10 power minus 6. It comes out 13.41 cm. So radius is half. A equal to 6.705 cm. In case of dominant mode, that is TE11, H11 prime is HA11 prime by A. It comes out 27.40. This figure, this value, one has to obtain from tables. The cutoff frequency then is this one, FC equal to H11 prime by 2 by root epsilon. It comes out 1.31 gigahertz. Bandwidth is 115% to 158% of cutoff frequency. So it is 1.50 to 2.06 gigahertz. D, WC 14. In this case, diameter, as we done in case of C, it can be found as 0.356 cm. Radius comes out as 0.178 cm. In case of dominant mode TE11, H11 prime becomes HA11 prime by A. It comes out to 10.34 into 10 square. The cutoff frequency then is FC. It can be found as 49.4 gigahertz. Bandwidth 115% to 158% cutoff frequency. It comes out 56.81 to 78.05 gigahertz. In calculating the diameter, in calculating broader dimension, we used 25.4. So what is this figure? You can understand by considering this table. 1 mil is equal to 0.00254 cm. Mil is 1,000th of an inch and 1 cm is of course 393.701 mil. So these dimensions, they come into those calculations. Now another problem, example 2. Determine whether the wave is TE or TM and frequency of operation for the following two cases. A, ZZ is 40 pi ohms, epsilon equal to 2.25 epsilon naught. B, ZZ equal to 150 pi ohms, epsilon equal to 4 epsilon naught. Solution. Here by comparing intrinsic impedance with wave impedance. By comparison, one can say whether the wave is TE or TM. Transverse nature of wave is determined. Let us assume F equal to square root of 1 minus FC by F whole square. A, ZZ, wave impedance is 45 ohm, epsilon is 2.25 epsilon naught. Now, intrinsic impedance is epsilon naught, that is 120 pi by square root of epsilon r. It comes out 80 pi. And 80 pi is more than 40 pi. Therefore, it is TM wave. Now, ZZ can be computed eta naught by square root of epsilon r multiplied by factor F. Therefore, F comes out to be 40 pi by 80 pi, 0.5. But F equal to square root of 1 minus FC by F whole square. So it gives F equal to 1.154 FC. B, ZZ is 150 pi ohms, epsilon is 4 epsilon naught. So intrinsic impedance in this case is 60 pi, it is less than 150 pi. 150 pi, it is given that wave impedance is 150 pi. Comparing these things, one can say it is TE wave. ZZ equal to eta naught by square root of epsilon or F. So F is 60 pi by 155, it is 0.4. From this one can find out frequency equal to 1.09 FC. We consider another problem, example 3. Determine guide wavelength, phase shift constant, phase velocity, group velocity, intrinsic impedance for an air-filled rectangular waveguide working at 25 GHz, assuming a cutoff frequency of 15 GHz. Guide wavelength, phase shift constant, phase velocity, group, these are all dispersion characteristics. Of course, intrinsic impedance, it is, we have to calculate in addition to these four quantities. Solution. As dielectric is air, lambda naught is lambda, V equal to C. Now let us define a factor. In the calculations, it is better first to have the value of F, wherever, because we need its value, we need to use this factor several times in the calculations, so better have its value computed first. And for the given operating cutoff frequencies, F comes out, FC is available, F is available, so it is 0.8. The guide wavelength is lambda G is lambda naught by square root of 1 minus FC by F whole square. So C frequency factor, it comes out 1.5 cm. The phase shift constant can be found as beta bar 2 pi by lambda G. 2 pi by 1.5, it comes out 133 pi radians per meter. Example 3, phase velocity is velocity by F. Velocity is C. Substitution gives 3.75 into 10 power 8 meters per second. Group velocity is Vg is Vf. V is C. Therefore, it comes out to 2.40 into 10 power 8 meters per second. Wave impedance, eta multiplied by F gives, for TM wave, eta by F gives for TE wave. Eta is eta naught as air is there in the waveguide. So it can be like this. Now another problem, example 4. A lossless 8 dielectric S-band waveguide with inside dimensions is carrying a wave. Its cutoff frequency is 4.87 GHz and operating frequency is 6.33 GHz. Determine propagation constant, guide wavelength, phase velocity, group velocity, wave impedance. Solution: as the dielectric is A, lambda naught is lambda, B is C. Now factor F we can calculate from the given values. F equal to, we can find 0.6388. It seems this 2 is superfluous. We can unconsider it. Next, A, propagation constant. Propagation constant is alpha plus j beta. We are considering lossless situation, so attenuation constant is 0. So propagation constant is simply j beta. Here j, it is dispersion medium beta bar. So 2 pi by beta bar is 2 pi by lambda bar or lambda g. But lambda g is lambda naught by f. So substitution results in j 84.69 per meter. Guide wavelength, this is guide wavelength. Lambda bar or lambda g, it is 2 pi by beta bar. Beta bar is already we have calculated. It comes out lambda bar equal to 7.42 cm. Phase velocity Vp is lambda bar into frequency. It comes out 4.70 into 10 power 8 meters per second. Group velocity is velocity multiplied by f factor f. V is available, factor f is available. V is equal to C because it is air filled. Vg comes out 1.92 10 power 8 meters per second. Wave impedance, transverse nature of the wave is not given. So wave impedance, it depends upon transverse nature. For TE, it can be found from eta naught by F as 590.15 ohms. For TM, it comes out, it is equal to eta naught F, comes out 240.82 ohms. Now another problem, example 5. A 25 GHz rectangular waveguide is filled with a dielectric having epsilon r equal to 4. Assuming cutoff frequency 15 GHz, find guide wavelength, phase shift constant, phase velocity, intrinsic impedance for TM21 mode. Now we first calculate factor F for 21 mode, TM21 mode, and it is a simple matter of substitution. It can be found equal to 0.8. The guide wavelength then is lambda g is equal to actually lambda naught by factor F, but lambda naught is V by frequency F, but V is C by root epsilon r. So substituting, we get ultimately this expression. Now given values, the already available values, using those available values, lambda g can be found as 0.75 cm. Phase shift constant beta bar is 2 pi by lambda g. It comes out 267 pi radians per meter. Phase velocity is Vp. Vp is V by factor F. V is of course C by root epsilon r. It comes out 1.875 into 10 power 8 meters per second. Intrinsic impedance, mode is given TM mode. So intrinsic impedance is eta naught F by square root of epsilon r mu r. It comes out 48 pi ohms. In the calculations, we assumed it is dielectric. Given that it is a dielectric, for a dielectric mu equal to mu naught or mu r equal to 1. So we used that fact in the calculations. While computing various quantities, he said it is clearly mentioned mu r equal to 1, root epsilon r equal to 2 has been used. Another problem, example 6. An X-band rectangular waveguide with inside dimensions 2.286 by 1.016 cm is filled with a dielectric material having epsilon r equal to 3. Determine wave impedance when frequency is 6 GHz, 12 GHz, assuming a TE11 wave and then TM11 wave. Wave number is given by this formula. Now, in case of 11, whether it is TE or TM, in case of 11, H11 square equal to pi by 2.286 whole square plus pi by 1.016 whole square. It comes out H11 equal to 338.38 radians per meter. Now, with this value on hand, let us move to A. In this case, frequency is 6 GHz. Omega square mu epsilon. So omega is available, mu is dielectric. So mu equal to mu naught, epsilon equal to 3 epsilon naught. So this quantity is available. We can compute by substituting given data, it results in 217.66 whole square. Now beta bar is omega square mu epsilon minus h11 whole square. So substitution results in J 259.01 radians per meter. Imaginary phase shift constant implies guide is acting as pure attenuator. No wave motion. Now we consider another frequency. B frequency is 12 gigahertz. Omega square mu epsilon in this case becomes 435.32 square. So phase shift constant, it comes out equal to 273.86 radians per meter. The phase shift constant is real. Therefore, wave is there inside the waveguide. So wave impedance in case of TE11 mode is omega mu by beta bar. In case of TM11 mode, it is beta bar by omega epsilon. Beta bar is available, omega, epsilon, all those things are available. Substitution results in ZZ 346.07 ohms in case of TE11 mode. It comes out 136.74 ohms in case of TM11 mode. These are some of the things which I want to share with you.